All right, I think we can get started. So I'll begin with introductions here. Hello and welcome. My name is Nick Brimley, and I am the director of the Slacksman Association. I will be moderating today's webinar, Rheological Properties of Slag and Aluminum Oxide Nanoparticle-Modified Cemented Paste Tailings. Our speaker today is Rauf Kafiani. He was a researcher in the environmental engineering at the University of Ottawa. His research focuses on sustainable cementitious materials, mine tailing management, rheology of cemented base materials, and the use of supplementary cementitious materials to improve the performance and sustainability of construction materials. He was also a Michael Thomas Research winner for SCA's 2025 Slag, Cement, and Sustainable Concrete Awards. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature, and we'll get to your questions at the end. And with that, I am happy to hand it off to you, Rauf.
Sure. Thank you, Nick. It's a pleasure having you here. You all. I'm going ahead to present my research. I'm very pleased that do you have my cameras on? Can you see me?
Yes, we can see your camera.
Perfect. Yeah, it was a very great pleasure to win this very precious and meaningful prize. My professor and all my research group was proud, and I received a very nice email from my professor, which was including the ACI is one of the best prizes one of the best organizations, and the prize I won is one of the most valuable prizes you can win in the cement industry. After that, I'm gonna start my presentation about the rheological properties of cement paste, backfill with iron oxide and aluminum oxide, nanoparticles. The presentation outline is first introduction, second research objectives, third materials and methodology.
Oh, Ralph, are you able to share your screen?
Oh, it's not shared?
Yeah.
Okay, hold on. There you go.
Perfect, we can see it now.
Awesome. Yeah. So the outline is first introduction, second research objective, third materials and methodology, fourth results, fifth discussion, sixth conclusion and future work. Sorry, seven references, and we're gonna start with introduction. The global Canadian mining industry. I'm gonna start with that. If you're not familiar with Canadian mining industry, so 25% of Canadian production of natural resources is gold, 14% coal, 12% iron, or 9% potash, so on. The mining industry has been very crucial for human civilization, and mining drives technical innovation through the extraction and processing the resources, and it has a very great impact on the economy. In 2020, and this is the picture of comparing 2020 with 2021, mining sector GPD in Canada, which increased. This graph shows the estimate of volume of tailing and waste rock produced in 2020. In 2016, the entire waste and the ore, the majority goes to waste, what we mine, and then a portion of it is ore, and then from the ore there is tailings, which is tailings are the process of extracting the minerals from the ore. A lot of portion of it goes to tailing, and we have to store this tailing somewhere. 69% of Ontario's, 69% of Ontario's, and 65% of Canada's underground mines use rock hydraulic and cement paste backfill. That's why it's very important for us to do research on it, because more than half of our tailings are stored as CPB. We're gonna improve the safety for the workers as well by making it more stable by increasing the shear strength and the duration of hydration, reducing the duration of hydration. So this is cement paste backfill technology, how it works. We store the tailings underground where we mine, which you're gonna use less, you're gonna pollute less of land, reducing surface disposal by storing it underground, enhance underground stability and safety. It's more safe when you increase the shear strength, actually, of course. If you can't see, it's 75 meters. It's usually like that. It's like a hypothetical number I use. Provides structural support, prevents collapsing, and reduce water. The ratio of water to binder, it reduces it. Rather than storing them on surface. This is a comparison of surface UPT, surface paste tailing, or CPB, which is cement paste backfill, cement paste backfill tail. These are the comparison. So this one, the CPB, uses less water than the surface paste tailing. There is gaps of knowledge in my research, which I'm gonna solve it. One of them is Portland cement contributing up to 8% of global CO2 emissions. So 8% of CO2 emissions of the globe, it goes to producing Portland cement, which is a lot. To produce Portland cement in general, like in total, 8% of the CO2 emissions is a result of producing Portland cement. So the less we use the Portland cement, the less we have CO2 emissions in the atmosphere. Cement can be constitute up to 80% of backfill materials, with CPB representing only 20% overall mining process. So this is how this research is gonna reduce the cement inside the backfills, which is a lot. Reducing cement content but by 1% can decrease total mining cost by 1 to 2%. Which is also a lot. You're dealing with like billions of dollars. 1%, 2% of billions of dollars is a lot of money. Prompting the search for alternatives to enhance CPB strength. And reduce carbon footprint. And this is my reference for it. Gap of knowledge. Again, nano iron oxide and nano aluminum oxide effect. So this is we don't know. This is the objective I wanna research for. Nano iron oxide and nano aluminum oxide's effect on CPB slag is unknown. It was unknown, now it is known. Slag and nanoparticles both reduce the flowability and I use superplasticizer to increase the workability or flowability, because when you use slag and use nanoparticles, the hydration process is faster. I'm sorry, when you use a slag, it balances out the effect of nanoparticles, which increase the hydration time really fast. I'm going to show it in the graphs and the results, but for now, we all know that the slag is going to delay the hydration, but I'm telling you, the nanoparticles is going to increase the hydration time. I'm sorry, decrease the hydration time, but slag is going to increase the hydration time. These are balancing out, but using slag and nanoparticles both reduce the fallibility. That's why I use superplasticizer. So everything is balancing out everything. So I'm going to show everything in the results. So we're going to go to research objectives. My research objective is to research and study evolution of rheological properties, yield stress, and viscosity, which both are considered as rheology properties, yield stress and viscosity both. And this is the general objective of my research. The specific objective is one, nanoparticles versus shear strength and viscosity properties of CPB made by Portland cement. Second is nanoparticles versus the shear strength and viscosity of CPB that contains slag. Third, nanoparticles vs binder hydration in CPB. Four, superplasticizer versus the shear strength and viscosity of CPB. The last but not the least is electron conductivity in CPB samples. Materials and methodology. These are the materials I used: silica tailing, nanoparticles, binder, tap water, superplasticizer. These are the schematics of them. The nanoparticle, iron oxide nanoparticles are looking like that. They're orangish, kind of brown. And then the nano aluminum oxides are very light, not in a pot, even a powder. It's like foamy thing. These are very highly dangerous for health as well, so I used all the protection and mask. These are cements. When you inhale them, actually, when they are in the binder, they're good, but when you inhale them, it's very dangerous for lungs. These are ions, that's why. Portland cement, we have slag, we have tap water, and we have superplasticizer. All the brands I use is on my references, so you can go and check. And tests, I use this yield stress, so I use vein shear stress, I use Wickham Friends vein shear approach. This is how it looks. There is a formula to calculate the shear strength based on what the number you read on it. So it's a process. And then viscosity, this is the machine I used for it. Brookfield digital viscometer I used. And then I use electrical conductivity monitoring, 5T electrical conductivity. This is how it looks like when I was conducting the test. And the rest is pH. So this is the pH meter used, and I applied TG, DTG, XRD, and zeta potential. I did zeta potential myself, which is this machine, Zeta Sizer Nano series. But for XRD and TG, DTG, I sent it away because we didn't have the instrument to use it, and some expert should do that. These are the materials. These are the blend weight ratio of Portland cement and slag and nanoparticles and everything. So for this one, CPB, the PCI means let me explain it like that. So for the first one, there is zero nanoparticle used in it. 0% of the binder. These are the percentage of the binder. I use 4.5% of the binder as a cement, and then binder as Portland cement, and then the ratio of water to binder is 7.8. And I didn't use any super plasticizer for the first one. For the second one, I added up 1% of nanoparticle, and then I added 4% of. But the binder percentages are all the same all through all the binders I researched, but the constitution inside the binder is different. So again, 4.5% of the CPB would be binder. Again, I used only cement in it. Same water to binder ratio for everything. So the binder percentage and water to binder ratio is all the same all through my experiment. For the first three samples, I didn't use any super plasticizer. My goal was to compare all the nanoparticles effect on my binder. So these are my first three samples, which is representing the PCI means I only use cement, 3% nanoparticle, 1% nanoparticle, and 0% nanoparticle. For the second two, I added super plasticizer to 1% nanoparticle and 3% nanoparticle. I didn't use super plasticizer with no nanoparticles because there was no point. So the other two is with nanoparticle and super plasticizer, and the rest is 50% slag and 50% cement with no nanoparticle. This is another sample. Another one is 50-50 with 1% nanoparticle. The third one is 50-50, 3% of nanoparticle. The fourth one is 25% of cement and 75%. So you see, I'm reducing the amount of cement gradually. 25% of cement and 75% of binder slag and 0% nanoparticle, and I increased the nanoparticle throughout this. So the last one I produced is 25% cement, 75% slag, and 3% of nanoparticle, which is everything in it to reduce the amount of cement. This is the final and last sample I produced. Material and this is the table of specimens and tests. I applied rheology, which is viscosity and yield stress. I I used microstructural analysis, which is TGA and XRD tests, and then monitoring, which is pH and electrical conductivity. This is all the tests I applied. You can see it in a chart. Now we're going to the result, the fun part. Um, Here you're seeing the first three samples with comparing how the effect of nanoparticles are. So there is no slack in these ones. They're all cement in the binder. 0% of the binder is nanoparticles. 1% of the binder is not of the CPB. It's of the binder. It is nanoparticles. These are iron. I show you both iron and actually iron and aluminum are kind of the same. So in this presentation, I'm going to show you only the iron, but the numbers are slightly different. Like the aluminum works better towards hydration. It increases the hydration higher. The shear strength, the yield stress, and the viscosity would be less, and shear strength would be higher. But the result is the same. It's slightly higher, very slightly, but the results are kind of the same. I used the iron for my presentation today. Anyway, so the yield stress, you see, it increases by increasing the nanoparticle. See, it's more than 600 Pascal for 3% of the binder, and we have 500 for none. The viscosity, so the viscosity is higher. The shear strength is higher and the viscosity is higher as well. It's because when there is more hydration, there is a layer of water. This is the effect. The layer of water would take over the machine's viscosity meter when it rotates. It's a disc which rotates. That's because it shows the viscosity more, but it's not actually in practice. So the yield stress and viscosity increase with longer curing transportation time. The mechanism is filter effect. This is the what I explained to you is a filter effect. Enhances cement's aeration, increase water demand, and it enhances folliculation. Fallibility or fresh CPB is altered by nanoparticles, iron nanoparticles. A higher dosage of iron nanoparticles intensify these effects. You see the pH is higher with more iron oxide. And the zeta potential is less when we use more nanoparticles. I mean, the less it is, it means that there is more ions are moving around. The more the pH is, the less the zeta potential value we got, which is aligned with the previous data and viscosity shear strength. The mechanism is by adding nanoparticle, coagulation happens. Sorry. I have technical issues. Oh, yeah. Yeah, so when the coagulation happens, the ions are canceling each other basically. So they cancel each other, then fall down, and they're not hanging out in the emulsion whatever it becomes. That's why the zeta potential goes less. Nano iron oxide VS versus the properties of sandwich packet in comparison all together. So this slag binder is more slag cement binder. These are comparing the samples with slag right now. This slag binder is more affected by nanoparticles over time. So the more nanoparticles we have with slag, see these are without these are viscosity and these are yield stress. We see the more the nanoparticles are, these are nanoparticle percentage. The gray one is with slag, 25% of cement and 57% of slag. You get the higher result of yield stress resistant in it. So the slag intensifies the effect of nanoparticles basically. The mechanism is friction effect of multivalent cation, because slag the particles are rough, they add up more fraction for, I mean, the more fraction, the more engaged, the more the particles are engaged, the more yield stress we're gonna get. And it dense, make it denser as well. The viscosity is less by adding the slag. I'm sorry, the viscosity is higher. I'm so sorry. The viscosity is higher as well, but less than, so in comparison of without, so viscosity is higher based on the nanoparticle percentage, but when we use slag for 50%, surprisingly, it's like the viscosity is less than all, and then the viscosity of 25% of cement and 75% of slag is higher than 50%, which the mechanism is because there is friction effect and the denser package. These two mechanisms cause the result that the viscosity in the samples with more slag is higher than the other one with less. But they're both less than the samples without slag. And then another mechanism is happens with slag is water cement ratio leads to more free water bleeding. So more free water, this last one cause how these two, the sample with more slag is more than the samples with less slag. The free water bleeding causes this. There is more free water bleeding in the last one. That's why the viscosity is higher. Based on the other two mechanisms, it had to be less. The viscosity had to be less, but because of the free water bleeding, is higher. This last one causes the higher density with the sample with 50% of slag. And then I'm gonna have this for this one. I brought the aluminum nanoparticles as well, so you can see it. Same thing, but same results as you see. The viscosity is here. My bad. I had to switch the graph of viscosity here and then the shear strength the other side, but yeah, it's opposite of the other one. This is we see the same results kinda for aluminum and viscosity. the shear strength and viscosity. The zeta potential of CPB made of cement paste, Portland cement and slag. So this is the zeta potential with slag, not with nanoparticles. Well, not with nanoparticles, which I showed you before. Which the more slag I use, the more coagulation and the less zeta potential I'm gonna have. And nanoparticles versus binder hydration in CPB is in respect to time of curing is so these are comparison of TG DTG in respect to time, 60 minutes and 240 minutes. We see the hydration is a higher. The more hydration happens, the more time goes by, which makes sense. This is like very obvious result. And then this is the interesting part. This is the ETG results for when you add up nanoparticles and slag. So with 50% of cement and 50% of slag, 3% of nanoparticles, and without the slag with 3%. So the nanoparticles here are all the same. I only changed the slag cement percentage in the binder. You see the more when you add slag, which the orange one is when you add slag, we have less hydration. But the red one, without slag, there is more hydration. So slag reduces the hydration process, which is also obvious. We all knew that before. Same thing happened. Oh, so the other one, I added. These are all 3% nanoparticles and 0% of slag. So the slag and the binder percentage are the same. The only thing I changed is the superplasticizer I add. So you see the more superplasticizer you add, so the red one is without superplasticizer and the purple one is without, it's with superplasticizer and the red one is without superplasticizer. So you see the hydration with superplasticizer is less in 2 hours. So all the results are in 2 hours. I didn't mention it before. The XRD, the TG-DTG results are within 2 hours. So the more superplasticizer we add, the hydration delays, which also makes sense. This last one is for the last one, I only changed the nanoparticle percentage. The black one is 3%, and I'm sorry, the yellow one is 3%, and the blue one is 1%, and the black one is without nanoparticles. So you see, the more you add nanoparticles, the more hydration you have. The yellow one with 3% and the black one with 0. Also in 2 hours. These are the results. You see, the intensified result means more hydration or more so more materials would produce with more hydration. The XRD shows you the materials within your sample. So the more material result of hydration we have, the more hydration we have, obviously. So this red one is 3% with 3% nanoparticles, which you see there is peaks, like the higher materials produced in the result of hydration, and with slag, same percentage of nanoparticles, but with 50% of slag, the hydration is less, is dumped. So the slag kind of balances out the hydration or decreases the hydration, but the nanoparticle increases the hydration. That's why the materials produced as a result of hydration are less in samples with 50% of slag. This one, these are without slag, but different percentage of nanoparticles. You see the black one with 0% of nanoparticles has less hydration, and the yellow one has more hydration based on that. The more nanoparticles we use, the more materials as a result of the hydration we have. So this higher peak one is CaCO3, and then this, I'm sorry, is CSH, the peak one. This one is calcium carbon oxide. This one. These are the CH, these two, and so on. These are the TGDTG results with comparison. So the nanoparticles are the same in these two samples. The only thing is different is 50% of slag. There is no slag in here. This is for, we had it for iron. Now this one is for aluminum, which also aligns with what we assumed, which the more when you add the slag, there is less hydration. The orange one is samples with 50% of slag, which has less hydration, rather than the red one, which has no slag. And these are with these are, everything is the same. We only added super plasticizer. When we add super plasticizer, the hydration is slightly less. And these are with the results of samples with different nanoparticles. The black is 0, the orange is 3%, and the blue is 1%. You see the 3%, which is the orange, is the highest hydration. The black with no nanoparticles of less, the least hydration. And then these are the results for an aluminum oxide. I showed you for iron oxide. These are for the aluminum oxide as well. The same results. I'm not going to explain everything again, because the results are the same. We only changed the nanoparticle itself, which was before it was iron oxide, and now it's aluminum oxide. This is the vein shear for aluminum oxide. I showed you before for iron oxide. This is for aluminum oxide, which also aligns with our prediction for 3% has more yield stress. And then the green one has these two samples. The green and the purple has 0. They have also super plasticizer, which the viscosity is less and the yield stress is less, with a very big gap, because super plasticizer decreases the viscosity and decreases the yield stress as well in respect to time. Eventually they're gonna get to each other, but 240 minutes they're super slower. Yeah. You see only 3% of aluminum oxide, you have more viscosity. But when you add super plasticizer to the 3%, which is the purple one, it's super slower. And then these are the same result for iron oxide, same thing. When you add super plasticizer to 3%, which is the red one, 3% with super plasticizer, which is the red one, both viscosity and yield stress decrease. And these are the electric conductivity of all the results. You see the first graph shows in respect to percentage of nanoparticles in binders. The 3%, which is the yellow one, has the highest electrical conductivity. It means that the ions are like very active in the process of hydration, which shows you this peak within, um, let's say 10 minutes, not 10, like 240 minutes. Yeah. Same peak happens in here. This graph, it's not showing in the legends, but I'm gonna tell you that the green is with 50% slag, with 3% of nanoparticles, but the yellow is only 3% of nanoparticles of iron without slag, which means the more slag you have, the less hydration you have because the activity of the ions are less. The last one, when you add superplasticizer, you see the superplasticizer decrease the electrical conductivity a lot. You see the gap is even more than a slag. With both 3% of nanoparticles. So this is 3% of nanoparticles with slag. The difference is with slag, 50% of slag. And this is without slag, but 3% of nanoparticles, but with superplasticizer. And then this graph is comparing 50% nanoparticle. These graphs are basically same results, but for aluminum oxide, you see same thing happens with aluminum oxide when you add slag. The hydration is less. The legend here is not complete. I'm sorry, didn't see that, but this is the purple one is 50% with 50% of slag with 3% of nanoparticles, but the red one is only 3% of nanoparticles. The third one is comparing the aluminum oxide nanoparticles 1%, 0%, and 3%. The black is 0% nanoparticles. The blue is 1%, and the red is 3% of nanoparticles. Without slag, you see the more nanoparticle you have, the more electrical conductivity you have. And then the discussion last. These are the numbers. You saw everything in graphs, but these are with numbers. The difference in viscosity is 16% when you add 1% of nanoparticle, and then the shear strength is the difference is 12%, and so on. When you add 3% of nanoparticles, the difference would be higher, like viscosity is. The shear is 15% now, and so on. The highest difference is 50% slag, 50% cement, 1% of superplasticizer, which is 24%, 1%. In the conclusion for future work, nanoparticles impact increases the yield stress and viscosity of fresh CPB. The mechanism is filler effect, enhances cement hydration, increase water demand and folliculation. For curing time, nanoparticles intensify with longer curing or transportation time. For binder type, the flowability with PCI in cement and Portland cement and slag binders are more affected by nanoparticles than samples with only cement. So when you add slag, it intensifies the effect of nanoparticles. The slag cement increase yield stress but decrease viscosity compared to Portland cement with higher binder content. Yeah. And then superplasticizer improve the flowability, which is obvious. Oh, it's very interesting that with slag and increases the yield stress but decreases viscosity. It's very good when you add slag. In conclusion, mechanical properties of these proportions of CPB would be the next step. Maybe somebody or me, if I have opportunity, would work on it. Scaling up lab results to larger scales. If someone is interested, you see like interest in the industry, work in the industry, we can do that. Analyzing cost benefit ratio improvement for practical use, which is also something that we can work on it. Potential benefits must be, of course, weigh against costs. These are my references, and if you have any questions, I would be available to answer.
Thank you, Raouf. And as you mentioned, yeah, if you have any questions, please feel free to use that Q&A section there. Yeah, send any questions you might have. Raouf, I got one question here. I know you kind of touched upon this, but what would you say like some of the biggest challenges or maybe takeaways you've had with your research, or anything that might have surprised you as well?
With my research, the biggest challenge was first when I added especially aluminum oxide to my binder. It was surprisingly dense, and it was like as soon as I added the aluminum oxide. So first I add the aluminum oxide to water with a specific machine. I forgot the name. If it blends everything, and then I add water with aluminum oxide to my binder and to my CPB. I'm sorry. As soon as I added the water, the specimen was super hard. It was like you're dealing with like 1 day specimen. You know, it increased the density, and you know what I'm saying. Like it was like you're dealing with a CPB that it was sitting there for like 2 days, and it was hard to conduct the experiments on it because the hydration was super fast. It was faster than what you think, and the machine was harder, especially for shear strength machine. It was harder to like conduct the experiment. This is one of them. The other one was, to me, the zeta potential experiment was very hard. Dealing with that machine was too hard. It wasn't like technical, but to me it was hard. Rather than that, I had to apply. I had to do experiments over and over. Like I got like off results a lot because when you do something wrong, or when you, so I was conducting the experiment like in 5 minutes, 10 minutes, 20 minutes, 1 hour, 2 hour. Sometimes I got off results a lot after like with a specimen of two specimens within 248 hours, especially with the experiments that I didn't have the test machines in the house. I had to send it away, so the result came back to me within a month, which was off, and I was like, okay, I have to do this again from the beginning, and then I get the right results within what I am expecting. So the other thing was time. Being these experiments very time consuming, and I have a lot of specimens, which was hard to like organize everything. Especially I had to make them dry after I do the rheology experiments to send them away for XRD and TG. Yeah, these are the hardest parts of my research.
Perfect. Well, if we don't have any other questions, I want to once again, let everyone know that if you're interested in viewing this webinar at a later time, it will be available on demand on the SCA website and our YouTube channel. And if you have any questions at all, please feel free to reach out to me at info@slagsmet.org. That concludes our webinar. I want to once again thank Raouf for presenting today, and I want to thank all of you for attending as well. Thank you, Raouf.
Have a great day.
Too. Bye.
Bye-bye.